So in the morning we saw how to use a library to handle the NumPy library in SciPy to handle numerical data. But sometimes we have mixed categorical data. So we may have strings and numbers and different categories and so on. And this library, Pandas for data analysis, Python for data analysis, the Pandas library, has some objects and many functionalities to make it easier to deal with data that is in tables, and the data can be of any type. So you can mix strings and numbers and so on. So we're going to see how to process that data and see some examples. So the two most important classes that we usually use in Pandas are the series and data frame. So a series, you can think of it as a column on a table. You have a sequence, an ordered sequence of values, but you also have an index, which is the index of the table. This index can be anything. The series can create a default index starting at 0, just like an array, but you can have anything as an index. So another way of thinking of a series is something that's similar to a dictionary, but you have an ordering of the values, and you may have repetitions on the index. But you have these two things, the index and the values. A data frame is a sequence of series, so you can think of them as the columns of a table, and they all share the same index. So a data frame is like a table where you have different columns and you can have an index or more. If any one of you already used R, the R language, this is based on the data frame idea of R. So you have this library that mimics those functionalities. So the series object is an ordered sequence of values that contains an index, and we can use the index to access the object. One way of creating a series, you import this class from Pandas, and then you use the class name, you give a series of values, and optionally you can create an index. So in this case, this series has these 4 values, 4, 7, -5, and 3, and each one of those appears associated with this index, with this character. You can also create a series from a dictionary, where the keys are the index and the associated values are the values. So basically, series allow us to correspond values with the index values. We can do most of the things we can do in NumPy. No, some of the operations depend on the types of values we have there, but Pandas is actually built over NumPy, so the same kind of functionalities are present. For example, we can compare a series with some value, and we get a series with the Boolean values resulting from the comparison. Note that this is not simply an array of false and true. We retain the same index. So this is useful because we can have in a series a subset of some values that we have on the table, and as long as the index matches, they don't need to be contiguous or to be in the same positions or whatever. Pandas can match them correctly. So the index gives us more flexibility to match the different values. And so these kinds of comparisons that we do with the series return also a series that keeps the same index. So we can keep track of the correspondences between these values and the index. We can use a series of booleans to index some series. So this CIR1 greater than 12, this expression evaluates to this series. This series has index and values, and these are boolean values. So Pandas will interpret this as asking for those values in the original series for which the values in the corresponding index are true. And we can use this to extract the values that we want. So in this case, 22 and 14 are the two values that make this condition true. We can do this with, for example, we can store this in a variable. So this is if you don't want to have very complex expressions, often we do this by steps. So we can create a mask of booleans and then extract the data that we want. So these are just a few examples for series. There's a lot more functionalities here, but I'm just giving you the introduction so you have an idea of how to use this library for this kind of data. The data frame, you can think of it as a number of series. Each series corresponds to a column, so the data frame is a table with one index and columns of values. For example, suppose we create this data frame, we have this distance column. We can create a data frame from a dictionary where each key is the name of a column, and then we have a list or a tuple, a series of values corresponding to the values in that column. Note that the table can have mixed values. So in this case, this would be a set of stars, the distance to the star, the magnitude of the star, and the spectral type. The spectral type is a string, and we have this table here. There are some advantages here relative to the NumPy matrix. One of them is that you can have mixed data types. The other is that you have this index, so you can create different indexes. You can have several indexes in a data frame. And another is that the columns have names, so you don't need to know where they are in the table. You can access them from the name. So, for example, suppose that we want the same matrix, but without the magnitude column. We can use this drop function. This will give us a copy or a view over the original table, but without this column. Typically, these operations in Pandas do not change the original table. They give us either a view, which is an object that is looking at the same data but only at a subset, or a copy of the original. Pandas tries to manage memory, so we don't always have complete control over what is a view or what is a copy, but we can check that, or we can force that. But in any case, in these kinds of operations, we are not changing the table itself. We are only looking at the table differently. So this would be the same table without the magnitude column. And we see here again the axis, because we can drop columns or we can drop lines, rows from the table. So if we are dropping columns, it means that we are going through the table along the columns and dropping those that match our criteria. So this is axis 1, which is in the direction of the columns. If we are dropping rows, we are going through the table in the axis 0 and dropping the rows with the index that matches what we give there. We can also access columns by the name of the column. So this will return a series. If we go into this data frame and we ask for the element distance, we get the column corresponding to that name as a series. So the index and the values. We can also use this lock attribute to access rows on the matrix. So for example, from our table, we want the rows for which it is true that the distance is greater than 100. So distance, star's distance is that series. Star's distance greater than 100 is a series with the same index but true and false values. So this can be used to access the rows on the matrix and on the table. And now we are accessing the rows by using this lock attribute, and we are looking only at the rows for which the distance is greater than 100. So this takes a bit of experience of trying out and doing some experiments with this until it makes sense and it's easy to use. But after you get some experience with this allows you to easily extract information from large tables by whatever criteria you have.
I'm just wondering, without the location,
Mm-hmm. What would mean? Well, without the lock, Pandas will try to interpret what you want, if you want the rows or the columns. But by default, it's expecting names of columns. It has some semi-smart code to try to understand if you want the rows and not the columns. But the safest way is, if you want the columns, if you are giving it column names, use just this way, and it will not make a mistake because it can identify the column names. So specific columns, but less than 100. So you want to join the two together? You could do it like this. So stars and then you use this and put a list of the column names, and then you put dot lock and the rows.
Model and therefore está accessing distance, Luisa, and Henry without a dot.
Yeah, if you do without this, like this, it may work if Pandas can figure out that you want the rows, so usually it works, but it's best to be explicit, because if you happen to have some index that has the same name as some column, then it may confuse the column with the rows or something like that. So if you do it like this, the library tries to figure out what you want, and by default it will try the columns. So if you're doing this on the columns, it works. If you want the rows, you can do it like this. It may work, but this way it's explicit. And it also depends on the versions. Sometimes you'll get a warning that you shouldn't do that, and so on. So this would be the standard thing. If you want columns, you index this way. If you want rows, you tell it to index this way. And this way you're explicitly telling the library whether you want columns or rows. Okay? Other than that, it changes a bit with the versions, and it may not work the way you want, because then you're giving the library the work to figure out what you want, and it may not reach the same conclusion. Okay. So there are many ways of accessing data. These are just a few examples. I'm going to show a few more in practical examples. Pandas is built on top of NumPy and Matplotlib. So these data frames in series include methods for plotting, and you can do box plots and statistics. More complex plots they have already implemented there, so you can look at the documentation, and it's easy to do data analysis with these libraries. We're only going to look at some details, but this is just to give you an idea of what you can do with this library. So let's start with one example. We can go to this site, baz.gov, which has records of public spending in Portugal. I think we can only retrieve 2,000 records at a time, at least when I downloaded this data set. This was the constraint. So in order to gather data in a larger period, what I did was I asked for 2,000 records starting on January 1st of 2015, and then from January 20. There is some overlap between the two sets, but I can then join them together and have a larger set of records. So this is just an example. If I wanted to gather more data, I could just ask for more and then glue everything together. What we get when we do these queries is a CSV file, with all these columns, so the type of contract, the type of procedure, what was the service that was contracted, and so on, and how much it cost, dates, and things like that. So what we can do is, after I downloaded the two files, so this one starts from January 1st and this January 20th, we have here in Pandas. I imported Pandas as PD. This is like what we do with NumPy, is another convention for using Pandas. And we have this function, read CSV. So Pandas has functions for reading Excel files, CSV, and those common formats. So if you have data in those files, you can look for the appropriate function, and this will return a data frame with the data that you have. So I'm going to read each CSV into a different variable, into two tables. Here I'm just specifying that the separator is this semicolon, which is a separator for the CSV file. Yeah. Oh yeah, you need to open it with a text editor. If you open with Excel, it will automatically convert into this table. But if you open either in Spider or in Notepad or something like that, you can see the actual file. Or if you have access to the documentation of the file, it will probably tell you what is the separator. So now we can see what we have in the data. After I run this, it's important in this case to keep this line, so don't delete it, because now we are dealing with data in Portuguese and we have all the special characters. So we'll need it in the source codes too, in order to write strings with special characters like that. But now I can, after running that, I have this temp table 1, temp table 2, so I can try in the console to see which are the columns. So this columns attribute of a data frame gives me the names of the different columns. This is an index object where we have the different columns here, including an index column that the Pandas created, and then everything else that we have on that table. We can also join the two together, and this is simple. We can use the concatenate from Pandas, the concat function. We just give it a list of which data frames we need to concatenate, and it will figure out if it needs to add columns or if it needs to put them in vertical, because we have column names and we have indexes. So if the data frames have the same columns, it will have to put one below the other to keep the same columns. If one data frame has a column that the other does not have, then it will have to add that column to the final data frame and include cells that have no values for those that don't have the column. So since we have column names and the indexes, this is all done automatically, and we can merge the tables together in this way. So this will give us the large table with everything, and now we can check for duplications. The reason we have duplicates is that we are reading these two files, and they have an overlap. So at the end of these files there is a set of records that is the beginning of the other one. So when we do this to check duplicates, we can have this duplicated, and it will give us a series, a Boolean series, so true or false, with a true marking any record that already exists on the table before. So if the values are equal to something that appeared earlier in the table, then it's marked true. So true are the duplicated, are those that repeat something that appeared before. And then we can use this value count. So this is a series, true or false, and the value counts method of a series returns a series with the index is all the different values that you have, and the value is the number of times each value occurs. So since this dupes series is just a series of true and false, the value count for this will be false and true. These are the two values that are present there, and these are the number of times they appear. So in these 4,000 records, we have 3,632, but then we have 368 repetitions of some other record because of the overlap between the two files. Or we can just do value count and then index the true here in this way. So this is one way where you can get the value from a series, which is by indexing through the index of the series. So this tells us immediately how many repetitions we have in this table, and to remove duplicates, it's easy. We can just drop duplicates from the table. So this is a common operation where you have repeated values, and the data frame has this method just to clean them out. Now there is another problem because yes. Yes, everything except the automatic index that the data frame inserts.
Part of the line was the same as
no, not part. It has to be everything. A duplicate is equal in all the values that you have there. So now another problem that we have is, even after dropping duplicates, we have a problem with the index in our table, because we loaded the first file, and Pandas added this index column first, just to give an index to the table, so 0, 1, and so on. And then we loaded the second file, and it did the same thing, 0, 1, and so forth. If we ask for a row given an index, we get two rows, because there is one coming from the first file and another from the second, and they have the same number in the index. So this is not very convenient, and we can fix that by doing reset index. So this will, Pandas will start 0 from the first row and then move on down from there, just adding 1, and we'll reset all the index. So after removing duplicates, we can reset the index, and now we have our table ready. We have one index identifying each row unequivocally, and we removed all the duplicates in the values. Now we can do something. For example, we can look at the price for each contract, and we see that it's in a very inconvenient format. So instead of putting a number there, what the people who prepared this table did was actually to write a string where you have a dot separating the thousands, and then you have a comma, and then you have the euro sign after a space. So we cannot use this as a number because it's actually a string with all of this. So I don't know if this was on purpose to make it hard to do statistics on the values, but anyway, that's the way the data is applied. But we can convert this into number by parsing these values. So let's take the price series, create a copy of this from the table, because usually when you do this, Pandas will either give you a view on the table, so you have an object that is pointing to a part of the table, or it will copy the table. This usually depends on the size of the table and memory management and so on, but it can happen that when you're doing something, it starts warning you that you have a copy of the table, for example. To prevent that, we will explicitly tell it to create a copy, and we don't get those warnings. And now, for each value in the index, so this is the index for this series, we're going to take the price there and split it on this space character and take the first part. So basically we are splitting here and keeping only the part with the number. And now we're going to replace the dot there with nothing, with an empty string. So we're going to remove this dot from the thousands, and then we're going to replace the comma here with the dot. And this way we get it's still a string, but it now would be, for example, 3500.00 without the euro sign and so on. And this is already a string that is in the right format to convert to a float number. So we do this and we put it back into the series. We're going to do this for all the values in the series. And then we're going to write into the table the same series that we changed with all these strings, but now converted to float. Since we retain the index here and we have the index in the table, Pandas knows where to overwrite the values, and so this way we replace these values by the actual numbers they correspond to. No, not a new column, to the same column. So we are overwriting the values there. Okay? Because we had the values in strings and we don't want them like this, we convert them to numbers and we put them in the same column, because now we have the price values in numbers. Okay? Yes, you could. You could create another column and put it there. That would be an alternative. But there is really no, in this case, we don't have any use for the values in that format because we cannot do any computations with them. Okay? But you could add other columns if you wanted to the table. Now this would be, you're copying the values, the original values, and then we are doing transformations on that series. But this is an intermediate stage, right? And now we just convert everything into numbers, and then we add it or to the same table, or we could create a different table and then add this series. So there are lots of things you could do here. In this example, I'm just replacing the values with a more useful one. So now we can check what we have on the table, and now we have numbers. We don't have those strings with the euro sign and so forth. And we can do this kind of statistics. For example, take the series with the contract value, the price, and check the maximum value, the mean, the median, and the minimum value. So actually we have here some cases with 0 in the contract value. And this is a bit strange to have these expenditures with 0 euros, but we can check which records are those. So this is This is the new index that Pandas created. This is the old index we had when we loaded the files. When we did reset index, it created a new one. And now I'm asking for those in the table, the values for which in this column they have a value of 0. So we have a series with the same index and true and false. And now I can check how many of them they are. So if you sum Boolean values, true counts as 1 and false counts as 0. So if you want to count the number of truths, all you need to do is to sum the values and you get the number of truths. But I can also ask for the table with a mask. So this is an example where I did not use the lock here. So I could do this explicitly by using lock and asking for that mask. But in this case, since this is a series of booleans with the index on the rows, Pandas will not confuse that with columns, and I'm pretty confident it will understand I want the rows. So this can be a bit risky in some cases. In general, it's best to be explicit, but in some cases it's easy to see that it's going to work because there is no way Pandas would confuse a series of booleans with 4,000 elements with just the columns, because that would not match. Okay. So in this case, I'm using that mask and getting the rows of the table for which this condition is true. So these are the 9 examples, the 9 rows in the table that have a value of 0 for the price. So this is actually longer because this has all the columns, and if you do this on the console, you get a large output with all the columns there. I cut it a bit, but just to give you an idea of how to check these things. So another thing we can do is to compute, for example, the cumulative sum of the cost during the period that I have here. So I get a series with the cost of the contract. I use this cumulative sum method in the series object, and then I can plot that. So this cumulative sum will also return a series, but just with all the prices added along the rows. And the series has its own plot method. So instead of using matplotlib plot, I can use the plot method here, and it will call the library. So if I want to plot the values in a series, all I need to do is to ask the series to plot its own values. And this is what I have. Here is the index for the series, and here is the cumulative sum that I got there. So if you want to visualize your data, it's easy just to use the methods on the series. You don't have to do it manually by separating the index into the x-axis and the values in the y and so forth. Now another example is to do histograms. Let's get all the contracts over 50,000 euros here. So this is the expensive contract mask. It has all those false and true, a series with false and true for this condition. And I ask from the table those that are true here. Now I can do a histogram, so I get this table. This expensive is the same sort of table as the original table, but only has the rows for the contracts that are expensive, that are over 50,000 euros. So if I wanted to check other things like the date of the contracts, who contracted who, and so forth, I would have all the information there. But now I can go to the column with the price and ask for an histogram with 50 beans. And this is what I get. So this is for the expensive ones. They go all the way to 2 million, I think. Yes. And from 50,000 to 2 million, and this is the distribution. And now I can do the same thing for those up to 50,000. These are the less expensive, and I can also do the histogram here. Sorry? Bin is the number of bars in the histogram. So the number of divisions that you use in the histogram. So if you use lower, you get wider bars, but fewer of them, and vice versa. Okay? So you can control that in the histogram, but you can also do that with matplotlib. You have the histogram there, but this is more practical when you are looking at series, because you don't need to worry about the x and the y and so forth. You just give the parameters that you want to change, and everything else is done automatically by the series. So let's see another example. This is one example for dealing with this sort of data. I'm just going to give a different one. This is a database of stars around our solar system, and we have things like the position in the sky, so declination, and then the distance to the star, magnitude, absolute magnitude, spectral type, and so forth. So to read this, again, we can use read CSV, and then we want to, let's do a plot with the magnitude of the 5 most common spectral types. So to get the 5 most common spectral types, we can use the value counts on the spectral types here. These are strings with different types with different spectral classes, and value counts will give us a series with each of the values and how many times it occurs in the table. And since this is sorted by the frequency, we can have the first 5 will be the 5 most common spectral types. So from the table we get the spect column. We use value counts on that series, and then we extract the first 5 from there. So this will be a series with the 5 most common spectral types. And now we can do, for example, histograms by selecting one of the spectral types. For example, the first one in this series would be the most common spectral type. So I'm going to look at the index in the count series. The index has the most common spectral type in the first position, the second most common, and so forth. So if I take the first element of the index on this count series, I get this K0, which is the most common spectral type. And now I'm going to go back to my table, and I'm going to get the absolute magnitude. So I get this series for this column. But then from that series, I only want those rows, those values corresponding to the rows where the star, in my table star data, the spectral type is equal to that most common. So you see here, I'm indexing the table by the name of the column to get the magnitude, but then from that series, I'm going to index it with a series of true and falses, where the true correspond to those stars with this spectral type. So this, let's go back here. The count, when I do counts, I get a series with the frequency, right? The first one is the most common. So I go there to the index and I get this K0, which is the first most common. Now here, star data, absolute magnitude, I'm getting this column from the table. But I don't want all the values here. I want those values for the stars that have this spectral type. So from this column, I only want the rows where this is true. And this condition goes to another column of the table, checks the spectral type. So I get the absolute magnitude of the K0 stars, only those. And this is also a series. So this is a series with the spectral magnitude, with the magnitude, the absolute magnitude of the K0 stars. And now I can compute the histogram, and I have the absolute magnitude histogram of the stars with this spectral type. Now, if I want to do the 5 most common, the histogram is not very good, because when I overlap histograms, then it's hard to see which is which. And in fact, I don't like histograms very much because of the binning effect. So we have all these bars. This is discontinuous here. So we're going to do kernel density estimation. This is a fancy histogram where instead of counting how many examples fall in each bin, we are going to create a continuous line by adding a kernel function in the position of each example. And a kernel function in this context is a continuous function that has an integral of 1, so the area under the line is 1, and it's symmetrical. We can use a triangle, a rectangle, a Gaussian curve, whatever, but as long as it's symmetrical around the central point and the area is 1, we can just add this one for each example and get a smooth line that serves the same purpose as the histogram, but it's nicer visually. So this would be the idea. Suppose that we have a distribution of 5 points like this. If we did a histogram, we could get a large bar here and smaller bars here. But if we use Gaussian kernels, then each point will contribute one curve that has this shape and it's centered on the point. Here, where the points are more separated, the sum does not go very high. But here, where they're together, when we add these curves, we have a larger peak here. And this is the idea of kernel density estimation. So we're going to use Gaussian functions. We have many different values of stars spread out over here of the magnitude, but we're going to add those Gaussian curves, and we get this sort of graph. So we can control how smooth the graph is by changing the standard deviation of the Gaussian curve, the width of the curve. But this varies continuously, unlike with the histogram where we have all these jagged bars. So we can do this with Gaussian kernel density estimation from SciPy. We don't need to implement this. We have this Gaussian KDE in the stats module in SciPy. And so to do the plot, we get our data, so the series of values that we want to compute the kernel density estimation for, and how many steps we want just to plot the graph. So this is just the number of points that we're going to use to do a smooth line on the chart. And I'm going to get the minimum and the maximum of the data, then create the x-axis here, so one series of values that is uniformly distributed between the minimum and the maximum with the number of steps that was specified. So for example, I want 200 points. This would be the 200 steps. And now I'm going to create this Gaussian kernel density estimator. So this is an object that this function returns. And I'm going to give it the data, because in order to compute the values on those points, this object needs the data, the distribution of the data points that I give it. And now I just compute the epsilon values on the values of the x. So what this object does is it has the distribution of values that I gave it, and if I tell it to compute the value in some specific point, it will add all the Gaussians there and tell me how much it is. So it's doing this operation for all the points that I have. And this is what I get here. So I get the epsilon values for drawing from the kernel density estimation, and then I return both things for the plot, the x and the y values. So now we can get the 5 top most common spectral types. For each type here, we're going to extract the absolute magnitude for that type. So we're going to the table and get the values for that type, for each of the types. Compute the absolute, the KDE plot with these values and 100 points to draw the line, plot it, and then draw the legend and save the picture. So this would be, we have the 5 most common types, and each one we have a representation of the distribution of the absolute magnitude with kernel density estimation. So this is better than histograms when you want to do overlap several plots, because with histograms it becomes harder, and also you have a smoother control over how smooth or jagged the chart is. Whereas in histograms, if you change the number of bins, you can change the bars very much from one step to the other, because it's discontinuous and not continuous. So to sum up, the idea here with Pandas is just in case you need to deal with heterogeneous data where you have strings and numbers and so forth, or if you have tables that you need to combine or load tables from different files, things like that, Pandas is very handy, because after a bit of practice you get lots of tools that make it easy to do what you want with the data. It's also useful when you want to do some quick visualization of the data, because if you want to look at graphs and means and standard deviation, things like that. Because you have everything implemented there, you can even do it in the console quickly and get a feel for your data. So this is specifically intended for data analysis, for if you want to explore the data before thinking about some more elaborate programs. This lecture is just a brief introduction, so just to give you a feel for the kind of things that you have, but actually this is a lot more than this. So one of the books I recommend is specifically about this library, and you have a whole book describing what you can do with this library.